Okay, welcome back, everybody. Welcome back to this afternoon's session. As our next speaker, I'm delighted to introduce Hasok Chang, who's Hans Rousing Professor in the Department of History and Philosophy of Science at the University of Cambridge. And he's going to be talking to us about measurement of unobservables through the ages.
Thank you, John. I have to say before I start, what a pleasure it is to speak at this HAPP event. Last time I was able to attend the HAPP event was almost 10 years ago, exactly, in its early days, and this and that have prevented me from being able to take part, despite Joe inviting me probably a dozen times for different events. So really pleased to be here, and I'm very impressed that people are back from lunch on time. I think my talk will connect well with what you heard this morning in the three fascinating talks. So I'm going to start with this theme of the importance of measurement, not quite like NPL for all of life, but at least in science. So here's a saying from Lord Kelvin, William Thomson, who said, "When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind." This was quoted by the famous Thomas Kuhn in one of his classic papers. And Kuhn tells you actually that this he saw not in Kelvin, but carved above the entry to the School of Social Sciences at the University of Chicago. So there's physics envy, right? Now, I think it is fair to say that quantification is pretty much the heart of modern science. And here's the great philosopher Immanuel Kant, who once said this. He said, when Galileo caused balls, the weight of which he had himself previously determined, to roll down an inclined plane, a light broke upon all students of nature. In the part that I skip, he talks about phlogiston, so I quote that in another context. And Torricelli, actually. But what Kant is talking about here is quite significant. So, okay, we're not entirely sure that Galileo did the thing of going up the Leaning Tower of Pisa and dropping balls, but it's that sort of thing that other people are talking about as well. How do heavy objects fall? But dropping different balls from the Tower of Pisa is not exactly measurement, right? What Galileo did in order to measure the phenomenon more carefully and precisely is to simulate a slowed down version of free fall by rolling balls on an inclined plane. And that he could time using a clepsydra, actually. And he confirmed that the distance covered was proportional to the square of the time elapsed. And that's what we still basically have. So when you can do this kind of thing quantitatively, imposing a coherent conception on the phenomena that we experience, that's what Kant was talking about in light breaking upon all students of nature. So measurement is crucial here. And I think there's a romance to it, right? This conference was billed measure for measure, so that's a literary allusion to comedy, a bit of tragedy, but this is romance, right? There are heroic stories of measurement that we hear through the ages in the history of science. I mean, what is Archimedes' eureka moment? That's density measurement. He figured out how to do it in the bathtub. Galileo, we already talked about. Jane showed one of Lavoisier's balances for measuring weight to track down chemical composition. She also showed the Michelson interferometer. People trying to measure the speed of Earth as it goes through the ether, which they couldn't ever do, and that, as you all know, led to Einstein's ideas about relativity. There are things like the cosmic background radiation, which was initially considered noise, and then precisely measured in terms of absolute temperature, and then theorized about in terms of the origin of the universe. So a theme that emerges, especially as we go into the modern era, is that with measurement, somehow we are learning about all of nature sitting in our tiny corner of the universe. But how is that possible? So here's an answer from another literary source, William Blake. To see a world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Easy for you to say, William. How do we do this? Holding infinity in the palm of your hand. And I think that is the kind of sense in which science has made progress in the realm of measurement, because what we often measure is something that is apparently unobservable. So what is measurement? I mean, we could have a whole lecture on that, but roughly speaking, let's say measurement is a quantitative kind of observation. But that means we have to be able to observe whatever it is that we are claiming to measure. But often, actually, the most precise measurements that we have in physics, the kind of thing that Richard told us about, they are of things that are not observable, if we mean by observable what we can directly perceive, right? Things like atomic weights, the ratio of the charge to mass of an electron, or Planck's constant. But also mundane things, right? We talk all the time about inflation, like that's something we can directly experience. No, because what is inflation? Inflation is change in the general price level. What is the general price level? It's not what you and I pay each time we buy something. There is no such thing, actually. The general price level is carefully curated and computed by economists by making up what they call the representative basket of goods. But you have to make a lot of decisions. Are we going to put cars in it? Yeah, but which one? Is it your Volvo or Vauxhall? Is it your sliced bread or is it your artisan sourdough, whatever? So that's not directly observable, yet we measure it all the time. We obsess about the numbers that we see in the news. Temperature, which I will talk more about later. Temperature is, of course, directly observable quality, let's say, hot and cold, but as a number, right? I do not sense 26 degrees. That is unobservable if you mean temperature as a number, and there's a whole story about how that was made possible. What about the size of the Earth? There's an interesting story, which brings us back to the kind of time that James was talking about. So this is a picture illustrating what is allegedly the first ever credible measurement of the size of the Earth, right? Eratosthenes, the librarian of the fabled Library of Alexandria, the man who is said to have coined the very term geography, right? He measured the size of the Earth by this reasoning. So legend has it that he was told that in Siena, which is current-day Aswan, on the summer solstice day, at midday, there were no shadows because the sun was literally directly above. Yet, sitting in Alexandria, he knew that on the solstice day, there was a shadow thrown from things. So he figured that must be because the surface of the Earth is not flat, but is curved. So if you measure the difference of the angles that the sunlight comes in at these two locations, and then you assume the Earth is a sphere, huge assumption, right? And then you measure the distance between Alexandria and Aswan, then you can figure out the whole area, radius and circumference of the Earth. So that looks very observable, but no, because the situation on the ground is this. You're not observing the sphere that is the Earth, as the flat earthers will remind you every time. And the distance between Alexandria and Aswan was measured by these poor people who walked, the bimatists who actually did pace-based measurements of walkable distances. And they must have been incredibly talented and disciplined people, because we're told that the number for the circumference of the Earth that Eratosthenes gave us is within 1% of the modern value. Anyway, so the size of the Earth is not a directly observable thing yet. Even in ancient Egypt/Greece, they figured out how to do this. Something that's more, in a normal sense, unobservable is, of course, atoms. So I want to show you just a snippet of how scientists learn to measure things about atoms, starting with weight. So that's John Dalton, almost exactly 2,000 years after Eratosthenes, his first book on chemistry, A New System of Chemical Philosophy, in which he gave us these pictures. These are his own hand-drawn pictures of atoms. Number one is hydrogen, 2 oxygen, 3 nitrogen, 4 carbon. It goes like that. And take note of number 37 there, which is his water. I'll come back to that in just a moment. And he gave us these physical views. This is a kind of thing I've learned from Robert Fox. And these are really weird pictures. First of all, you notice his hydrogen was not H2. It's just single atoms of hydrogen atoms, neatly stacked up, not bouncing around at random, and so on. And why are the atoms hairy? The hairs are his attempt to represent what he called the atmosphere of caloric. Caloric being the substance of heat. If you want to know anything about caloric, talk to Robert Fox, who's given us the definitive history of the caloric theory. But I want to focus your attention on weight. So this is somebody's convenient tabulation of the atomic weights that Dalton gave us in his successive publications. So 1803 is a manuscript source, 1808, so on, are the successive parts and editions of his chemistry text. Now have a look. You can read that in the back, right? How many did he get right? 1. He got hydrogen, but that's cheating. Because that's just 1 by definition. Until the modern metrologists changed that. So the so-called father of chemical atomism couldn't get a single atomic weight right. And that tells you, first of all, how hard it is, because he had no access at all to the individual atoms. And if you look at the numbers more carefully, you see he was not just wrong. He was not randomly wrong. He was wrong in a promising kind of way. So look at carbon and oxygen, which he had as 5 and 7. If his experimental technique had been better, he would have given us 6 and 8. So half of what we now believe. Why? Well, here's a deep philosophical problem. What do we know from actual hands-on measurement in the lab? Dalton and fellows could determine, right, the bulk weight with things like Lavoisier's gasometer. They knew that 1 gram of hydrogen would combine with 8 grams of oxygen. Yeah. What does that tell you about atomic weights? Nothing at all, unless you know the molecular formula, right? So now we think water is H2O, 2 of hydrogen, 1 of oxygen, which means that the weights of the atoms are in the 1 to 16 ratio. right? But it's also possible that water is HO, as Dalton thought, and the atomic weights are in the 1-to-8 ratio. Who knows? This is what philosophers of science call the problem of underdetermination of theory by evidence. Because the actual evidence we have is 1-to-8 gross combining weights. Yeah? So how do you break this circularity, which Dalton, being the smart man he was well aware of. And he said, I solve it this way. He said, I adopt what I call the rules of greatest simplicity. He said, water is the only compound I know of made up of hydrogen and oxygen. Hydrogen peroxide had not been discovered yet. And he said, basically, to paraphrase, why would God have made it in a more complicated way when it could be a one-to-one combination? So he assumed the molecular formula for simplicity and then could deduce atomic weights. So that's just a little snippet to tell you that what I've been calling observability in the broader sense of being able to observe something with the help of instruments and theories and so on, that is an achievement. It's not something that's predetermined out there without us involved. Observation, observability, measurement, it involves inference based on theoretical assumptions, and that is how, to borrow Blake's phrasing, we hold infinity in the palm of our hand. But it could go wrong, as it did in the case of Dalton. So that's the sense of the heroic adventure that I want to convey about measurement. It's not given to us. We have to work at it, and sometimes we can make it work. And when I'm being more philosophical in my work, what I worry about is the kind of operational coherence of these activities through which we make measurement. It's roughly speaking the sense of things fitting together. Right? And there's a long story of that in this book I published about 20 years ago, which is all about how thermometers are made. And I'm not going to have time to give you much of the details of what is in this book. I want to do two things. One is to give you a flavor of the issues involved by telling you how I got into it, and then very quickly I'll mention a few of the issues that the scientists were dealing with. So this is how I got into it. You know how these standard everyday kind of thermometers are made, right? This is the typical thing they would have used in the 18th and 19th centuries. How is such a thing graduated? So we'll fill a glass tube with a particular kind of liquid. We're going to plunge that into a vat of freezing water. We're going to see how far the mercury or whatever you put in it comes up. We're going to mark that 0. We're going to put it in boiling water next, long before triple point and such things were known. We're going to see how far that comes up, mark it 100, and then we're going to divide the interval between the 2 points equally. When we do that and call the halfway point 50, we're making a significant assumption, right? That the liquid you're using comes up exactly halfway by volume, 200, when the actual temperature is 50 degrees. How do we know that? Well, give that question to the GCSE physics student, and the student will tell you, we do experiment, we check it out. We plot temperature against volume, we see if the points lie on a straight line. Yeah, good answer for GCSE, but how are we going to get the temperature values in these experiments when we haven't already got a thermometer that we trust? There's a really annoying circularity here. And I was thinking about this just in a philosophical way, and I decided I can't solve this problem. But then I thought, if you ask the physicists today, Oh, well, they will tell you, no, we know mercury doesn't expand exactly linearly with temperature. We know exactly how it does expand. So I thought I have to look at the history. Who figured this out and how? And that's how I ended up writing this whole book, about which I'm not going to tell you. Because I've got 10 minutes left, and there are other things I want to tell you. But there were various attempts made, and in the end, after 150 years of very smart people arguing about this, the problem was put to rest by the great French experimental physicist Victor Regnault, who said, do not try to solve this problem. You can't solve it. Instead, what you do is make a practical thermometer that will be self-consistent. So with his criterion that he called comparability, he said, so previously mercury had been touted as the best thermometric liquid. Regnault said, well, let's see about that. So he made a bunch of mercury thermometers, calibrated them in the same way with the same 0 and 100, and he showed that they didn't agree with each other in the middle and beyond. Why? Because glass behaves in erratic, unregulated ways. The glass envelope changes volume in a way that you can't control. So he said, forget that. Instead, we use air thermometers. Why? Because the expansion of air is so much greater than the expansion of glass, you can safely ignore the glass problem. But that's not really satisfactory, is it? So that's where William Thomson comes in, which I'll show you in just a moment. But before Kelvin, Jane showed the Wedgwood pyrometer, right? So the famous Potter Wedgwood really did invent this thing, with which he measured temperatures. As Jane briefly mentioned, he did connect his scale to the Fahrenheit scale using silver as an intermediary. Anyway, he got these wonderful temperature numbers. I mean, he's interested, of course, in the top item, which is how hot is my kiln, because he couldn't know it, and he knew that his wares were being spoiled for lack of precise temperature control, but any thermometer he would try to use would just melt, and that's why he came up with these refractory clay pieces mixed with alum, which would contract in what he thought was a regular way, but the same problem as before. How did Wedgwood know that the contraction of clay was linear with temperature? And we now say, no, it isn't. So Wedgwood was very unlucky in working in the low end, where the thing looked linear, but then its behavior changes. So he got these kinds of numbers. He said his furnace was 21,877 Fahrenheit degrees. And you don't have to know a lot about temperature. We say now that the surface of the sun is about 10,000 Fahrenheit. So these numbers were way off, but how do we know that these numbers are wrong? And there's a whole other story in which there were actually many different ways of measuring these extremely hot temperatures, and most of them agreed more or less with each other and disagreed with Wedgwood. So as I put it, they ganged up on Wedgwood, declared him wrong, and the other methods right enough. And then there's a whole other issue that I deal with, which is, so far it's all very empirical. But where's the theory of temperature? And William Thomson was very dissatisfied with that state of affairs. He said, a fundamental quantity like temperature should not be defined with reference to a particular physical substance like air. Echoes of today's meteorologists saying we shouldn't do this material thing as our standard. So Kelvin was already thinking like that in 1848. I mean, look at his date. He's 24 years old. He's already been professor of natural philosophy at Glasgow University for 2 years. Anyway, in 1848, he defined absolute temperature in a completely abstract way using the Carnot cycle. To cut a long story short, that's all fine, but nobody knew how to make a Carnot cycle in a good enough way. It's a highly idealized system. Actual systems behave nothing like the Carnot cycle. So how do you do it? There's a whole paper that I published about that, if you're curious. He said, no, we're going to make an air thermometer with actual air. And what we know is that if we had an ideal gas and made a thermometer with it, it would read absolute temperature. But we don't have an ideal gas, so he said, we'll use an actual gas, we will correct it using the Joule-Thomson effect. But then Joule-Thomson effect, as some of you know, is a temperature measurement. What do you measure that with? You have to measure that with a normal thermometer. So then you have to come back and correct the correction and do this iterative process, which they did. Okay. And that's all I'm going to say about temperature because I only have 4 minutes. The last story of measurement I want to tell you is this. It's not about the building. It brings me back. It's about Robert Millikan and his measurement of Planck's constant. But Millikan, in my undergraduate days at Caltech, trying to study physics, Millikan was the library. So we said, yeah, let's go to Millikan. Millikan made the first precise and respected measurement of Planck's constant, and he did this in 1916. If you know your dates, you know this is full 10 years before Schrödinger's equation. So he measured Planck's constant before there was quantum mechanics as we know it. He did it using Einstein's equation for the photoelectric effect, right? Photoelectric effect in which you shine ultraviolet light onto a metal surface and electrons jump out, right? So what Einstein said is each photon carries this amount of energy, which he expressed as Planck's constant times nu, the frequency, and that energy is given to the electron, and the electron comes out with the energy that the light gave it, minus W, the work function, which is the amount of energy that the electron requires to free itself from the metallic surface. So that's that equation in the blue with W as the work function. So Millikan thought, okay, I can measure Planck's constant if I would do several instances of the photoelectric measurement, right? And plot K, kinetic energy of the electron, against the nu, the frequency of the incoming light, and the slope will give me H. It's beautifully simple in conception. I mean, highly theoretical, but beautifully simple, but not so simple to execute. So his idea was that these electrons would be coming off the metal surface with a certain energy, and he would put an electric field against their motion to stop it. So if the electron has, 5 electron volts of energy, you put 5 volts of potential against it, and it should stop, right? So a steady electrostatic field, and Millikan noted how far these electrons could swim upstream in the potential gradient, as it were. And that's what he did in this apparatus shown here, which he called the machine shop in vacuo, because he wanted to do the experiment in an evacuated chamber, which is what you see on the right-hand side. The little cylinders, these metals that he was using to emit photoelectrons, but if the metal surfaces were oxidized, then it messed up the result. So he had this knife thing in the vacuum evacuated chamber to shave off the metal surface right before the measurements were taken. So that's the thing anyway. And there's a Faraday cage and electric potential put on it. So the idea was, I'm going to see where the electrons stop, And what he did was he measured the current of photoelectrons being received in the right-hand side chamber. And ideally, it would go to 0 when you have just the right amount of potential. Of course, that never happens. There are always stray effects. So what he got were these graphs, so that each graph is for a certain frequency or wavelength of the incoming light. And what he did, because the 0 point was very uncertain, he took the values of photocurrents, certainly not 0, at different voltages, and he would extrapolate towards 0 current. So with the intercept, he could find the value he wanted. But then what he found out is that many of these graphs had long feet. They only approached 0 very slowly. And he said, I'm just going to cut the feet off. And I believe that part of that decision, that decision partly helped him eliminate quantum effects, which he wasn't thinking about, but never mind that. So he did the plot that I initially mentioned of the slope of which gave the Planck constant, and it was an extremely precise value. So to come back to my original question, but how is this done? Holding infinity in the palm of your hand. It's done with a lot of theory, a lot of experimental ingenuity. You have to master the materials and hope for the best, which in Millikan's case worked out. Now, I am out of time, but I cannot resist telling you a little joke before I go. So this was a joke that we had when I was an undergraduate, going in and out of Millikan Library. And so story goes like this. A bunch of students are given this task. We give you a barometer, and with that, you have to measure the height of Millikan. So one student, of course, goes up to the top and using the correlation between air pressure and height, computes the height of Millikan. Another student says, you know that relation is highly unreliable and depends on all kinds of situations. So he said, I'm going to do some real physics. Tied the barometer to a long string, made a pendulum, went to the top of the library and measured the period of the pendulum from which they could deduce the height. Another student looking at it said, why do you bother with that? Because you just have to measure the length of that string. That's the height of the library. But then you're not really using the barometer, are you? And then another student came and said, no. Also, it's not right to do this other thing. I'm just going to purely use the barometer, not even a string. So that student went to the top of the library, dropped the barometer, measured the amount of time it took to crash to the ground. And while all this is going on, another student had a better idea. Ran to the custodian of the building and said, I'll give you this shiny barometer if you tell me exactly how tall the building is. And you can guess who got the best answer. And there's always the human element. Thank you.
Thank you very much, Hasok. Yes, so I see a question here.
That was truly inspirational. I shall go and read your book. You said at the very beginning romance. So, does romance have an atomic number, and how would you measure its temperature?
I think romance has many atomic numbers. I mean, that is the history of chemistry, right? There's the romance of helium, finding it first in the sun and then locating it on Earth. There's the romance of radium and Marie Curie. There's the romance of carbon. Gold, of course, and mercury. So how do you measure it? Like anything else, with a lot of hard thinking and good luck and material help.
Okay, I'll take this person first, and then
Thank you. I wanted to ask a question about the recent discovery on the exoplanet K2-18b. So it's a question about scientific certainty. So I think there were
Sorry, the recent discovery of?
Potentially of a water world teeming with life.
Ah.
Okay, so it's about possible discovery of life on an exoplanet. Could you just explain to us what 3 sigma means in terms of certainty around those results, and perhaps give us a flavour of the feeling at Cambridge about whether the team have actually, nailed it, or is there still, a lot of doubt?
Yeah, I certainly can't speak for the rest of Cambridge. You'll have to ask other people about that. The sigma issue is a big part of the story of measurement that I left out, right? So the sigma measures give you a sense of how likely or unlikely it would be for you to have got the result you got if your idea is not correct, right? To put it roughly. And this is where, standards differ from field to field. The particle physicists insist on 5 sigma, and a lot of other people would be very happy with a lot less than that. But, it's a whole question of error. How do we deal with error? And something I didn't mention is, there are 2 kinds of errors, right? There's systematic error and there's random error. Sigma and so on, the statistical techniques mostly help you with random errors, right? If you've got systematic error built in your theory or your fundamental material setup, then there's nothing that can help you, right, except bitter disappointment later on down the line. Thank you.
you next.
So part of this question of how you can do this, how you can see the universe in a grain of sand, is if you think there are physical laws which are absolute. So part of this is the development of physics to say there are universal laws. But I could also say sometimes that doesn't go, someone mentioned GPS, and the problem there is what relativity tells you is actually distance and time are not well-defined quantities when you measure well enough. So in some cases, you may just find the thing you're trying to measure actually isn't physically defined in the end. So the only things you really can hope to absolutely measure are the ones where you think physical laws guarantee that they're correct.
Mm-hmm. And my view, personally, is that there are no absolutes in science. That's almost the definition of science to me. Nothing is beyond question. I think Carl Sagan once said, the only sacred truth in science is that there are no sacred truths. But there are many things we have to take on faith, really, to be able to get on. And the assumption that there are regularities in nature is one of them. The assumption that our fundamental constants are constant is another one. Now, we could wake up one day and find that the speed of light has gone haywire. We don't think it's likely, but, that is a logical possibility. So how do we deal with it? I think that's where the humility comes in. We get on the way we do because that's the only way we can, but we assume that's always fallible. But the question is, what else is there? What other options have we got except to proceed in this way of empirical science? I mean, regarding GPS, it's not as haphazard as it sounds at all, right? I mean, they know the general relativistic and special relativistic corrections that have to be made.
No,
they make those.
that's true. We think that is a physical law, but it's just telling you that the concepts you thought were trying to measure aren't actually what you thought they were.
That's right.
Thank you. Yes.
Yes, this is excellent. This is in the realms of philosophy and metaphysics, I think. I think you alluded to it. You didn't mention it, but I think you were alluding to William Ockham when you say the simplest solution is the best. And it clearly wasn't when he was looking at the atomic Dalton, wasn't it?
Yes.
Weights. Is there any truth in Ockham? We like to have simple things, but maybe we oversimplify things. I'm sure there are lots of examples. I mean, Newton was very right till Einstein came along. Is there is this just a human trope or way we think, or is there something fundamental in nature that makes us want to simplify things? I mean, I'm really running out of words because it is a very deep thing. But we want to put something into an equation that is a model of what the universe is, but maybe it's a bit more complicated than that.
Yeah.
I don't know really how to put that in a question, but
I think I get
if you can talk about it, because I think
get it.
You were touching on that sort of thing I'm talking about, really. Yeah.
I think there is something in nature that drives us towards simplicity, but is in human nature. Yeah, I mean, we like simplicity for very practical reasons. And by practical, I also mean the practical necessities of theorizing, right? Now, with vastly increased computing power, these days certain scientists are abandoning this criterion of simplicity. They say, we will just crunch numbers, right? Or we will just go out and sequence all the genomes there are. So simplicity, I think, is a contextual virtue. It's not always a virtue. I think people misuse these ideas of Occam's razor. No, simplicity isn't always the best assumption, but I think Dalton's case is very telling. He was very conscious that he was adopting these rules of simplicity without an absolute guarantee that this was the correct thing to do. He did it he did it because that was the only way he could get on. And then because he got on in this imperfect way, chemists could learn other things with which they could come back to Dalton's starting point and correct it. But if Dalton and others had never ventured because they were uncertain, we wouldn't have got anywhere. I think that's the point. Yeah.
Thank you very much. I have to draw questions to a close now and do the changeover, so we ought to thank Professor Chang as well.